Hello students, my name is Hitesh Jindal, and in this lecture 4 of Electrostatics part 1, we'll be discussing about electric dipole. What is an electric dipole, right? And what are its electrical effects in its space, right? So we'll be talking about the electric field due to electric dipole at various important points, right? So this will be talking about in this session. Let me have a presentation to be shared with you. So as you can observe in front of you that we'll be discussing about electric dipole and the associated physical quantity, right? This is a physical quantity associated with electric dipole. So what is this electric dipole moment, right? And then as I have told you that electric dipole, as you can see from the name, it suggests that an electric dipole, right? You see electric. So electric means charges, right? So electric comes from charge. And what is dipole? Having two poles. So in electrostatics, we have studied that charge has two polarities, right? Charge may have two polarities. It may be a positive charge, it may be negative charge, right? So dipole means a system, an electric system having both the poles, right? So this is a kind of system, right? We are having positive and we are having negative, right? It is like separated with some distance. So that is an electric dipole, right? A positive charge, a negative charge, right? So that becomes an electric dipole. We have various electric dipoles in our nature, right? So as you can observe from this example that if I'll talk about this compound HCl, right? So it is having H plus and Cl minus, right? So this is an ionic compound, right? So there is a little separation between them. So if I talk about H plus, so there is a little separation between H plus and Cl minus, right? So this becomes positive pole, this becomes negative pole separated by a distance, a small distance though, right? So this becomes an electric dipole. These kind of systems will be studying, right? We'll be talking about that H2O is also an electric dipole, right? Then we'll be talking about the electric field due to dipole, right? At various points. So most importantly, we'll be talking about electric field due to dipole at axial point, right? And at equatorial point. Right? Then we'll be talking about in this series only we'll be talking about the torque on dipole, right? If dipole is kept, if dipole, and also one more thing, dipole is represented by an arrow, right? That will be talking about. So when it is placed in a uniform external electric field, right? What is the torque that the dipole experiences, right? Then we're talking about the equilibrium state of the dipole in an external electric field, right? So we're talking about stable equilibrium, unstable equilibrium, right? Then we're talking about the work done, right, in rotation of dipole in electric field, right? So in this, we'll be observing that some concepts of our work energy, right, will be applied. We'll be talking about that work done by a conservative force is equal to the negative of the change in potential energy, right? That will be talking about in here. So this concept, this equation comes from our work energy power in our 11th grade, which we studied. Then we'll be having this SHM of dipole in uniform electric field. And then how dipole interact, that we'll be talking about, right? So we'll be discussing all these topics. The topic of electric dipole we'll be talking about as per our CBSE requirements, right? So as I've already told you that what is an electric dipole? Electric dipole is a system, right? It is a system, electric system having two equal and opposite charges. The charges are equal, right? If this is +2, so this would be -2, right? The charges are equal but opposite. Both the poles are there in the system, separated by a small distance. This small is important, right? The small is keyword here. The distance must be small between the two charges, and that is called an electric dipole. As you can observe from this diagram, that we have a negative charge -q here, we have a positive charge +q here, right? And there's a separation d. This is the separation, this is the small separation, right? D. So this system is an electric dipole. Now an electric dipole has what? An electric dipole has electric dipole moment, right? That is denoted by this symbol vector p. It is a vector quantity, right? Electric dipole moment, right? So what is this electric dipole moment? What is this physical quantity, right? That we'll be talking about in the next slide. So you see this electric dipole moment, as it is a vector quantity, as it is a vector quantity, right, has what? Has direction. So we need to understand the direction of electric dipole moment. So that is from two directions as possible, positive to negative or negative to positive. So this dipole moment's direction is from negative to positive, right? So this is the direction. This is the direction, as you can see from this arrow, is the direction of electric dipole moment from negative charge, right? This is quite important. It is from -q to +q, right? From negative to positive. All right. Then we have electric dipole moment as the physical quantity. So we have discussed the direction of it. But what is the magnitude of electric dipole moment, right? What this physical quantity signifies, right? What it consists of. So this physical quantity is a combination of, you can see, the magnitude of one of the charges. So we have +q -q. So we just take the q, right, the magnitude of one of the charges, and we multiply it by the separation, right? And in this electric dipole, in the system, we have only these two things. We have one of the charges and we have a separation. So we multiply that, and that will give us the information about the electric dipole as a system, right? This physical quantity represents that, Q into D. Great. So this is important. This expression is very important, and this definition is very important from the point of view of our CBSE, right? So electric dipole moment is the product of magnitude of either charge, one of the charges, and the separation between the charges, right? So the magnitude of either charge or separation between the charges, that is known as the electric dipole moment, and the direction is from negative charge to positive charge, right? Great. Now what is the unit of electric dipole? What do you think? You see, as we have seen above, electric dipole moment P, it is denoted by small p, is charge into the separation D, right? So you see here, charge is represented by which unit? In SI, right? Let's say we are talking about in SI. So it is in coulombs, right? And this is distance, this is length in meters. So the SI unit is coulomb meter. Great. What is the CGS unit of electric dipole moment? It is dB, right? It is this dBi. It is dBi, right? So 1 dBi is equal to 10 to the power -10 into 10 to the power -8, right? So that will be doing. So you just need to, no need to have a very much knowledge of this magnitude. You just remember that CGS unit of electric dipole moment is dBi. It is not in NCRT, so we need not be very worried about it, right? All right. So this will be considering, right? The SI unit of coulomb, this electric dipole moment is coulomb meter. Great. All right. Then you see here, let us move to this question, right? If we say that determine the electric dipole moment of the system of three charges, right? So we have this equilateral triangle. You can see L, 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 right? So we have to find the electric dipole moment of this system of three charges. So we have seen that two charges constitute an electric dipole, positive, negative. So for solving this question, we can consider this as a combination of two electric dipoles. You see, this minus q, this minus 2q, I can write as minus q and minus q, right? So I can have this combination plus q minus q, right? I can have this combination plus q minus q, and one minus q is here, right? You're getting it, right? At the same position almost. So you see, this is the dipole moment here, right? This is the dipole moment here. Obviously, they'll be having different directions, right? So if this is the magnitude of this is p, no, right? So this would also be what, p, right? Because separation is L, charge is same, right? And p is equal to what? P is equal to q into L. That we know. That is simple, right? So we have two dipole moments here, p p. So you see, we have two vectors here, p p. What would be the resultant, right? We have to find the resultant. So what we do? We complete the parallelogram, and this would be our answer. This would be our net resultant, right? This would be the our electric dipole moment of the system, right? We can say p net, right? And what would be its magnitude? How will we find its magnitude? So we know that as it is an equilateral triangle, this angle is 60 degree, right? This angle is 60 degree. So this, as these two are equal, so this must be 30 degree. You're getting it? This one's 30 degree. So this must be the p net, right? This should be 30 degree, right? And what would be its magnitude? You see, what would be its magnitude? So p net, you see, should be equal to under root of p square plus p square plus 2p square cos 60 degree. Cos 60 degree is half, so we'll be having, you see, root 3p, right? And we know that p is what? P is q into L, right? So p net would be equal to root 3q into L. And what is the direction? You see, it is in the negative y direction, right? So what we'll be putting? We'll be putting minus sign here and j cap if I want to represent the vector form of it, right? So we'll be having our answer as C, right? Okay. Then we are having this thing, that electric field of an electric dipole for points on the axis of it, right? So this is very important. So you see here, so let's say we have one charge like this and another charge like this, right? And let's say this is an electric dipole, right? Okay. Now I'll consider this as the midpoint of their separation. So that means if I'll take, so I'm taking this distance as, let's say, L, and this distance as also L, right? So the separation becomes 2L, right? So the dipole moment here, let's say I'm defining the dipole moment, that would be in minus q2 plus q in this direction, right? So this would be dipole moment in this case, right? So this P, how would I define it? I would be defining it as q into 2L. Great. Okay. Then what do we mean by finding electric field for points on the axis? So this is the axis. You understand? This is the axis of the electric dipole, right? This is the axis of the electric dipole, right? Now we have to find the electric field at any point. Let's say I'm measuring the distance from here. So I want to find at some separation r, I'm calculating the distance from this midpoint, right? From this midpoint of the separation. So let's say this point is P and I want to find the electric field here, right? What would it be, right? So what would I do? I would be finding, so we have two charges here. So I'll find electric field due to plus Q separately, minus Q separately, and then I'll do the vector sum. Superposition principle that I'll be doing. Okay. So what about the electric field to plus Q? In which direction? It would be in this direction, right? It would be somewhat in this direction, right? So that would be the electric field due to our positive charge. Great. And what should be its magnitude? So E positive should be equal to K Q by, what is the separation? You see, the separation is, can I say that it is L plus R, right? Can I say that? It is L plus R square, right? Now you see, what about due to minus Q? So it should be in this direction, right? E minus, and what should be its magnitude? So this E minus must be, you see, K Q by, right? This distance is R, right? And this is L. So we'll be having R minus L whole square, right? So obviously from these expressions also, right, I'll be able to tell mathematically that this E minus is greater than E plus, right? For this situation, for this point, right? For P, for point P, right? This must be the case, right? Because you see denominator is less here, right? Numerator is same in both the cases. All right. So that means the net electric field should be in this direction. E net, right? E at point P should be in this direction. And which is this direction? This is the direction of the electric dipole moment, you see. Getting it? And how would I find the answer to it? Right? How can I find this EP now? So this EP, the value, the magnitude of a direction we have got, right? So it becomes E minus E plus, right? So this is what you see, KQ. So I'll be putting 1 minus R minus L whole square minus 1 upon R plus L whole square, right? So then you see, I'll be getting this thing, KQ, right? Then we'll be having this thing, the LCM. So we'll be having R square minus L square ki ka square, right? Obviously, can I do that? Right? Can I do? Right, yes. And here I'll be having, you see, 2 RL from here minus, and then minus of 2 RL, right? Doing 4 RL, right? So we'll be having like this KQ 4 RL by R square minus L square whole square, right? So now you see here what is my P? My P is this. My P is, you understand this, right? P is Q into 2L, right? So we have here, you see, we have here Q, and we have here 4L, right? So we'll be writing it like this. You see, 2 KPR, right, upon R square minus L square whole square, right? So this would be the electric field at that point. Getting it? At the axial point, right? Now we can have a very special case here. We can have a special case here that, let's say my R is very much greater than L, right? The special case that, let's say this distance R is very much greater than this L. So that means I am finding the electric field at a very far away point from the dipole, right? So this means that at a far away point from the dipole, so in that case, dipole is considered as short dipole, right? So I can also say that, let's say, or for short dipole, right? And it can be represented by an arrow, right? It can be represented by an arrow. So we have our dipole moment here, right? P, and then I'm finding at a distance R at some point with the electric field. You're getting it. So in this case, my R is very much greater than L. So this becomes my short dipole, right? This becomes my short dipole or a point dipole also. We say it up sometimes, right? So what is the electric field in this case? So you see here, what can I do in this expression? So is so r square would also be very greater than L square. So we can ignore it, right? So we'll be having this the electric field obviously would be in this direction only, right? Uh, E at axial, right? So would we, you see, we can neglect L square in comparison to R square, right? So in this expression, what would we have? So we'll be having 2 kpr by r ki power 4, right? So finally we'll be having 2 kp by r cube. Getting it? 2 kp by r cube. So that is electric field at the axial point. Getting it? All right, all right, right. And what about this? What about this point? What about any other point? So in case I am taking the point to be here, this side. So here also the electric field would be in this direction only, right? Let's say this point is P dash, right? So this electric field at point P dash would also be in this direction. P dash would also be in this direction, and same expression holds. So that means at axial point, the direction of electric field is in the direction of electric dipole moment. Getting it? So also here for short dipole, I can represent it as a vector quantity, that vector E axial. You see? So to show the direction in the direction of dipole moment, I can write it like this: 2k vector P by R cube. So that means my electric field at any axial point is in the direction of dipole moment. Getting it? All right. So this we have already seen that the electric field due to a dipolar distance r on its axis is inversely proportional to what? Proportional to r cube, right? For general point charge, electric field is proportional to inversely proportional to r square, 1 upon r square, right? Here it is 1 upon r cube. So that is to be considered, right? Okay, right. Now, now what about electric field for point on the equatorial point, right? So we also say that on the equatorial line or axis, equatorial line. So what do we mean by equatorial line, right? So it is like this. So let's say we have plus q here, we have minus q here, right? And this is the separation. And again, this is the midpoint, right? This is L, this is also L, right? Now, this line, if I draw perpendicular bisector here, no. So this line is known as the equatorial line, right? Now, here what we have to do is we have to find at a distance r from this point, right? So let's say the point is here now, and I want to find the electric field at this point, right? So how to go about it, right? This is the equatorial line. So this question, this derivation is also important. Both these derivations on the axis and on the equatorial line, very, very important. Both these derivations, right, are very, very important from the point of view are CBSE board examination, right? Every year, generally it comes, right? Okay. So how to go about it is, I'm just giving you an idea that from with respect to plus q, right? You see, electric field must be in this direction. So this I can say that it is due to E plus, right? And due to this negative charge, you see, where should be the direction? It should be in this direction. Getting it? E minus. Getting it? Now you see. Now you see here. this is an isosceles triangle, right? This is L, this is R. So this would become under root of R square plus L square. Same this. So distance is same, charge is same. So E plus, the magnitude of E plus should be equal to the magnitude of E minus. Let's say should be, it is E, right? And as both are of the same magnitude, right? So you see the resultant must be like this, right? EP. The resultant must be like this. Getting it? And what is the angle between them? What do you think is the angle between them? You see, this is 60 degree. No, this is not 60 degree, right? What is the angle between them? So how do we calculate that? Let's say this angle is theta, right? This angle is theta. So this angle should also be theta. Getting it? And if this is theta, so then you see this is theta. Getting it? So this E cos theta, this E sin theta, you see, we have the components here then. Right, let me show you. So here we have in here E sin theta, right? I am considering E plus as E, right? Considering this as E. And we have E cos theta. And again from this here E sin theta. And again we are having in here E cos theta. Getting it? So here we are having 2E cos theta, right? And this would cancel out. This would cancel out. You see? So our EP here becomes what? 2E cos theta. And what is E? E is this. E is this K Q by this square, right? So this square means R square plus L square, right? And this cos theta. What is cos theta from here? You see, cos theta is L by this distance. So L by under root of R square plus L square, right? So you see here, we have what? We have 2, we have Q, we have L. This is what P, because we know that P is equal to 2QL, right? In this situation. So we can write it like this. So the EP becomes what? EP becomes KP by R square plus L square की power 3 by 2. Okay, getting it? And you see the direction of EP here. The direction of the electric field at an equatorial point is, this is the direction of electric dipole moment for this case, right? This is the direction of electric dipole moment, right? Vector P. And you see the direction of electric field is anti-parallel or opposite to this direction, right? So also in this case also we consider these cases that, let's say, R is very much greater than L, right? Or we can say for short dipole, right? For short dipole. And that is represented like this, that we have like this as short dipole, and I want to find at some distance R, we want to find the electric field. So that would be in this direction, right? Getting it? And this is the short dipole we're talking about, right? So this is the equatorial point. So this E equatorial here, this E equatorial here should be what? Should be, you see, we neglect here, right? L square is neglected in comparison to R square. So we'll be getting R square by 3 by 2. You see, KP by R square की power 3 by 2, right? So 2 gets cancelled out. So we'll be having KP by R cube. Getting it? And if I want to write it in vector form, right? So I'll be writing vector E equatorial is equal to minus K vector P by R cube. Very important. Because the direction of the electric field at an equatorial point is opposite to the direction of electric dipole moment. Got it? Right? So you can see for short dipole, no? For short dipole, so for short dipole, you see what we have. We have vector E axial as 2k vector p by r cube, right? And vector E equatorial is what? Minus k vector p by r cube, right? So this becomes very important expressions for our examination point of view, right? Very important, right? So in this case, you see if both of the cases the r is same, so you can also write it like this. You can also write it like this, that vector E axial, I can say that, is equal to minus 2 times of vector E equatorial, right? So this might come in one marker MCQ, right? All right, right. So you see, then we have this thing, this question you can see here, that due to electric dipole, the electric field intensity we have to find is parallel to dipole axis, right? So parallel to dipole axis. So it is in the equatorial case, it is anti-parallel, right? So vector in equatorial case, the vector E and vector P are anti-parallel. So I can write down here the vector E and vector P are anti-parallel in this case, right? Okay. So you see, we have a dipole here. This we have minus q, this plus q. So this is the direction of dipole moment. Getting it? This is our vector P. Now it is saying that electric field intensity parallel, where it is parallel, right? So obviously P point is axial point. So electric field here would be in this direction, EP. So this is parallel at P. What about at point Q, right? So let's say this is point Q. So the electric field here should be what? The electric field here should be in this direction, right? EQ. So anti-parallel, right? So parallel is at P only, right? At Q, if I want to write, so I'll write at Q, vector E is anti-parallel, to vector P, right? So that we need to write. All right. And what about torque on electric dipole? So this concept is related to this, that let's say we have an external electric field. So I'll be just summarizing it for now. And let's say I have an electric dipole placed like this. So this is my positive charge, negative charge. This is my, let's say, positive charge. And this way we are having an electric dipole. All right. So this is the dipole moment, vector P. And this is the external electric field, right? External. This is known as external electric field, right? So, and this is making this angle theta here. So this dipole will be experiencing a torque, right? In, like in this direction, to be experiencing a torque, right? And that torque, the value of that torque is should be equal to, you see, vector P cross vector E. Right. So thereby we can find the direction of right hand rule. Vector P cross vector P. So it will be rotated like this. Right. And its magnitude then becomes what? PE sine theta. PE sine theta. Great. All right. Then we have SHM of dipole, right? So this again comes from this fact that, let's say I have this way, I have this electric field, right? and I have a dipole placed like this. Let's say I'm taking a dipole like this, right? This is a dipole, right? So, okay. So what happens in here? No. So this was, let's say if the dipole is placed in this manner, no. If theta, in this manner, if the dipole is placed, so then it is the stable equilibrium position for it. Now, if it is displaced, right? Now, if it is displaced uh, by very small angle, let's say theta, right? So this is my electric dipole, right? P. So now, if it is displaced and then released, right? So it will experience a restoring torque. So that tau restoring should be what? That tau restoring should be what? Should be equal to P E sine theta, right? And that should be the negative sign because theta is in this direction and torque is having in the opposite direction, right? And for small theta, right, small displacement, we know that sine theta becomes equal to theta. So I can write it like this, that tau restoring, right? Tau restoring can be written as what? Tau restoring can be written as I alpha, right? So you can write I alpha is equal to minus PE theta, right? So my alpha here becomes minus PE by I into theta, right? Then I'll compare it with the angular SHM equation minus omega square theta, right? So if I'll compare this equation by this equation, you see, so I'll be having this PE by I. I is the moment of inertia here, right? Moment of inertia of this dipole. So would be equal to omega square, right? So that means my omega becomes equal to under root of PE by I, right? And so what is the time period then? So time period is obviously equal to 2 pi by omega. So this would be an SHM performing, right? This dipole would perform an SHM here. So it would be 2 pi under root of I by P, right? So this would be my time period. And the frequency of oscillation, obviously, I know that frequency is 1 by T, right? So that would be 1 by 2 pi under root PE by I, right? Getting it? So that we need to understand. All right, right. So this is a question we are having in here. So I'll suggest you to please perform this question as a homework, right? So you can please take a screenshot, right? And please perform this question as a homework. So this is based on this SHM thing, right? That you need to cover it. So I'm just telling you the approach that we have an electric dipole, separation D, charges have same mass, right? So it is kept in a uniform electric field, it is slightly rotated, then its angular frequency you have to find, right? So we have already done that, right? Omega is, we have already got that omega is under root of, you see what we got? PE by I. And what is P? P is, you see, P here is Q into D, right? So what do we write? So we have PE by I. We need to find I also. So this P is QD. So we'll be writing QD into E by I. Now what is I here? That you need to find out, right? If both have the same mass, that obviously center of mass about it will rotate. So it would be D by 2, right? So the moment of inertia would become, right, M D by 2 square plus M D by 2 square, right? For both the masses, so it would be MD square by 4 into 2. So I think that would be MD square by 2. So that you'll be writing here under root of QDE by I is, you see, MD square. So MD square by 2. So 2 will go up and DD will get cancelled. So we have 2 QE by MD, right? So we'll be having 2 QE by MD. So this would be our answer. All right. All right. Then we have this question, simple. We have a dipole moment given, right? We are given, so you see, so you have to find the givens, right? So this is what? This is our P. What is this? This is our theta, right? Then we have, this is our E, right? We have to find the torque. So torque we need to find as PE sine theta, right? So that will be performing at home. All right, right? Then what about the maximum torque? You see, this question is about the maximum torque. So what about maximum torque? I'm just letting you know the concept of it. So tau is what? Tau is PE sine theta. This is for general theta, right? A general orientation. Now, when do this value of tau becomes maximum, right? So sine theta would be maximum. So tau max would be when sine theta will be max, right? Sine theta should be maximum. And sine theta is maximum when it is 1. This that value is 1. So means theta should be pi by 2. So at pi by 2, we have tau max. And at uh, tau max should be P into E. So we just have to multiply the dipole moment and the electric field, that becomes our maximum torque, right? So if external electric field is like this, right, then this position, right, this position of the dipole would be considered as pi by 2, right, as the situation having the maximum torque, right? So in this situation, it will be having maximum torque, tau max. Getting it? All right. Then we have potential energy. This is also, we have an expression here. For potential energy, we are having, it is minus vector P dot vector E, right? So that by thereby it will become minus PE cos theta, right? So this is the potential energy of electric dipole in uniform electric field, right? So we have many more things to be covered in here, right? You see, we have few questions. We have then work done in rotating dipole from stable to unstable equilibrium. Let me tell you what is the stable equilibrium. So this, if you have electric field like this, right? If you have electric field like this, right? So then this position, as I have talked about, for theta is equal to 0 degree. So that is a stable equilibrium position, right? But when we have theta is equal to 180 degree, right? Pi, let's say it is kept like here. So dipole is kept like this, P, right? So then this angle between the electric field becomes that pi. So this situation is unstable, right? Unstable equilibrium. Obviously, it will not be experiencing any torque in this position because sine pi is 0. But if it will be displaced, if it will be disturbed, right? If it, let's say it will be disturbed by a very small angle, right? If it will disturb at a small angle, so it will go like this then, right? It will be rotated like this then. It will not come back to this position. So that is why it is unstable equilibrium, right? All right. And in calculating the work done, no, what we need to understand is we need to apply that formula, that work done is equal to negative, or work done by external agent is equal to negative, or is equal to change in potential energy, right? That is P final potential energy, final minus potential energy at the initial position, right? So that we need to find out. It is negative when we need to find the work done with the conservative force. Then we have this negative change in potential energy, right? All right, right. So all these things we have discussed, right? Electric dipole moment is what, right? Then the electric field of a dipole, right? At a general point is not in our CBSE syllabus, right? So we just have to focus upon the axial point and the equatorial point, then the torque and also the potential energy, right? In the coming lectures, I'll also talk about much of this work done and the torque aspects, we'll be talking about it a little more, right, in the coming sessions. So the next session, that would be our next session of this electrostatics part 1, I'll be discussing about the Gauss law, right? So we'll be discussing about the Gauss law and the associated electric fields due to various charge distributions, the application of Gauss law, and then again we'll be reviewing the entire chapter, right? And then we'll be looking at few important questions, right, and the important derivations which will be coming in our CBSE board's perspective, right? So thank you for now, right? So I'll be seeing you in our next session. Thank you.